A skydiver of mass 76 kg is falling vertically in still air. At time t equals 0, the skydiver opens his parachute. Now figure 1.1 is the speed time graph for the skydiver from t equals 0. So you can see speed is on the y-axis, time is given on the x-axis. So this is the speed time graph. Now, using figure 1.1, that you have to find the deceleration of the skydiver immediately after the parachutes open. So see, we can take, since it is saying immediately, so we can take this triangle where time is 0.5 seconds, and we see the change in velocity. So this is around 59 and this is 40. So change in velocity will be 59 minus 40. So that is 19 meter per second. So the change in velocity is 19 meter per second, and the change in time delta t we have taken that at 0.5. So this, as you can see, this delta t equals 0.5 seconds. So the deceleration, to calculate deceleration, is change in velocity upon change in time. So 19 upon 0.5, which is 38 meter per second square. So the value of deceleration is 38 meter per second square. The force due to air resistance acting on the skydiver immediately after the parachute opens. Now see, force is basically F. See, the formula is F is equals to m into A, where m is the mass and A is the acceleration due to, not due to, A is the acceleration which it is undergoing. So this is 76. Now see, acceleration is 38 meter per second square, as well as you have to include g in this. So this acceleration must contain g, as that skydiver is overcoming that, taking g as 10. So 76 into 48, solving it, substituting this in the calculator. So 76 is the kg and 48 will be the acceleration. So this is 3648 Newton. So the force is 3648 Newton. Explain in terms of forces acting on the skydiver, his motion between t equal to 0 to t equal to 6 seconds. So now as we can see, the deceleration, this skydiver was going deceleration, means that deceleration was decreasing, and ultimately when the upward force, the air resistance, becomes equal to the weight, then it attains the terminal velocity. So now what you will write is that the answer is that upward force is greater than the downward force, hence there is deceleration. So as soon as it opens the parachute, the upward force is more, or the air resistance is more than the weight, hence it deaccelerates. But ultimately the time will come when the two forces balances each other. Yeah, upward force is greater than downward force, hence there was deceleration. Now after some time you see that when the two forces, the air resistance and its weight, which is the downward force, becomes equal, that skydiver is going to attain the terminal velocity. So now here you can see this is the deceleration, and this is also going decreasing till the velocity becomes constant. So now when it reaches the terminal velocity, you can see from the graph, when it reaches the terminal velocity, you know what happens? The air resistance, or the upward force, is equals to the weight, which is the downward force, weight of the skydiver, which is the downward force. So when it reaches the terminal velocity, the upward force balances the weight. Explain why opening the parachute cannot reduce the speed of the skydiver to 0. You see, the air resistance on the parachute is because of the speed of the skydiver. So if the speed becomes 0, the air resistance will become 0. And also there is a constant downward force, weight, acting, which is the weight. So what you will write is that The air resistance on parachute. The air resistance on parachute is because of the speed of the skydiver. If the speed is 0, skydiver. If the speed is 0, there will be no air resistance. And also there is a constant downward force, which is the weight of the skydiver acting. A constant downward force, which is the weight. If you like the video, please do like and share it with your friends. And to score good marks, do subscribe and press the notification bell icon to all to watch our latest videos. Thank you. Figure 2.1 shows a wooden trolley of mass 1.2 kg at rest on a rough surface of a bench. You can see this is a trolley, and a ball of mass 0.52 grams travels horizontally towards the trolley. The ball embedded itself in the wood of the trolley. The trolley moves with an initial speed of 0.065 meter per second. Calculate the impulse exerted on the trolley. We know that the impulse is actually force into time. Now impulse is force into time. Also impulse is equals to the change in the momentum of the body. So here we will take it as a trolley. So impulse is basically will be the change in the momentum of the trolley. Change in momentum of trolley. So that is m into delta v. Since m remains the same, the mass of the trolley will remain the same. You have to find delta v. Delta v is the change in velocity. Delta p of trolley means the change in momentum of trolley is equals to m into delta v. Delta v is, we know that since the trolley was initially at rest and then it starts moving at 0.065 meter per second. So delta v is same. We take the delta v as 0.065 meter per second. So delta p of trolley will be m times delta v. So substituting the value m as 1.2 kg and delta v as 0.065. This will be 0.078 kilogram meter per second. So impulse is 0.078 kilogram meter per second. The speed of the ball as it hits the trolley. Now see, the ball was initially at rest. So you have to find its velocity, taking this as v. Now we know that by the conservation of momentum, initial momentum equals to final momentum. We know that initial momentum of the trolley was 0 as it was initially at rest. For the ball, we will take the initial momentum 0.52 into v, which is equals to the final momentum. So final momentum, we know the ball gets embedded inside it. So v takes the total weight. So this is 0.52 gram, but this is 1.2 kg. Converting this to grams is 1200 grams. So the total mass will be 1200.52 grams. So 1200.0.52 into, now both are moving with the velocity same velocity 0.065. So v will be this 1200.52 into 0.065 divided by 0.52. Substituting the values in calculator, you get the velocity as 150.065 meter per second. Now you can round it off to 150 meter per second. So hence the velocity is 150 meter per second. As the trolley moves across the rough surface, it slows down and stops. Explain in terms of work done the energy change that takes place as the trolley slows down. So in that, we know that as the ball gets embedded inside to it, the trolley has the kinetic energy. So trolley has kinetic energy So because of kinetic energy, it moves. So the trolley has kinetic energy. Trolley gains kinetic energy as it moves. It does work in overcoming the friction between the ground and the trolley. So it does work in overcoming the friction, because of which it loses kinetic energy in overcoming friction between the ground and the trolley, because of which it loses kinetic energy, which becomes zero after some time. Because trolley is going to be ultimately is coming to at rest. And also in this process, some thermal energy is also produced. So in this process, some thermal energy is also produced. Now explain in terms of molecules why liquids are very difficult to compress. So see, in liquid, molecules are very close or they are almost touching each other. Hence, the space between them is negligible. So in liquid, molecules are very close. You can write almost touching each other. Hence, the space between them is negligible. And also, the repulsive force between the molecule is also very large, so which makes it like very difficult to compress. And the repulsive force between molecules is very large. Hence, difficult to compress. Next part. In figure 3.1 shows the device that uses liquid pressure to lift heavy boxes. As you can see, boxes, cylinder, piston, oil, and there is a pump which actually pumps the oil. Now the boxes are fitted by pumping oil into the cylinder. The force upward on the piston due to oil and the force downward on the piston due to the air above the piston combines to produce a constant force of 8800 Newton. The pressure of the air is 1.0 into 10 to the power 5 Pascal and the cross-section area of the bottom surface of the piston is 0.016 meters square. Calculate the pressure of the oil at the bottom surface of the piston. See, now we know that the pressure is because of two things. It's at the bottom of the surface is mainly because of the oil. So pressure PB we are writing for the bottom, and this is for the air pressure and for the oil, pressure due to the oil. So basically now calculating pressure due to the oil, pressure is force upon area and the force applied is 8800 Newton and the area is 0.016 meter square. Solving this, you get 5.5 into 10 to the power 5 Pascal. Now also there is an air pressure from above. Air pressure, this is 5.5 into 10 to the power 5 Pascal. Now PA, we are calculating PA. PA is the pressure due to the air, which is 1.0 into 10 to the power 5 Pascal. Now we have to add these two. So 1 into 10 to the power 5 Pascal plus 5.5 into 10 to the power 5 Pascal. That gives you 6.5 into 10 to the power 5 Pascal. 10 to the power 5 Pascal. That's the answer. As the boxes are lifted, the depth of the oil increases. Explain why the pump must exert an increasing pressure on the oil as the depth of the oil increases. See, we know that pressure equals to force upon area. So if you see force is equals to pressure into area, that means to increase the force, the pressure has to be increased. And we know that in liquid, as the depth increases, the pressure increases. So that's why. So see, yeah, the force will increase when the pressure increases, since the area remains the same. And the pressure will increase, so hence the depth has to be more. Because the pressure in liquid depends upon the depth. So what you will write is that an extra force is to be applied to lift the box up. Is to be applied to lift the box up. To lift the box up. Now, since pressure increases, force will also increase. Now, as the depth of the oil increases, the pressure increases. Pressure increases. Hence the force which is to be applied will also increase. Hence the force will increase. Suggest one reason why the force of 8800 Newton in B cannot lift boxes of weight 8800 Newton. The thing was that both the forces were balanced. These two forces were balanced. Okay, so the forces were balanced. So at least some initial upward force greater than 8800 Newton is to be applied. So initially, the upward force initial upward force greater than 8800 Newton has to be applied to start the motion. That's what you will write. That will be your answer. Start the motion. An aluminum saucepan with a plastic handle contains cold water. Now figure 4.1 shows the saucepan on a hot plate. As you see, aluminum saucepan, water, hot plate, plastic handle. State why the pan is made from aluminum but the handle is made from plastic. You know that, see, aluminum, the pan is made from aluminum because aluminum is to be kept on a hot plate. So that's why that pan is to be made from aluminum. Aluminum is a good conductor so that it can conduct the heat from hot plate to the water. And also since we use handle, so that's why the user should not feel very hot or it is difficult to handle. So plastic handle is made because plastic is a poor conductor, so it will not going to conduct the heat, hence that remains cold. So that's why plastic is used. Now why plastic? Because plastic is a poor conductor. Or you can write plastic is an insulator. Both are things, same thing. The hot plate is switched on, and as the temperature of the water increases, the internal energy of water increases. State in terms of molecule what is meant by increase in internal energy. Now see, molecules, internal energy is basically the kinetic energy of the molecules. So when you heat any substance, its molecule starts moving vigorously. So molecule starts to vibrate vigorously, and what happens is that the kinetic energy of molecule increases. So molecule starts to vibrate vigorously, because of which the kinetic energy of molecule increases. Of molecules increases. Explain in terms of atomic lattice and electrons how thermal energy is transferred through the aluminium. See, atoms touching the hot plate. Okay, atoms touching the hot plate starts to vibrate faster. Now these atoms, they pass their energy to the neighboring atoms or electrons by colliding with them. Now start writing. The atoms touching the hot plate starts to vibrate faster. So these atoms pass on energy to the neighboring atoms or electrons by colliding with them. So these atoms pass energy to neighboring atoms or electron by colliding with them. Now these electrons pass energy to other atom and other free electrons. Now these free electrons pass the energy to other atoms when they move through the lattice. So this is how the energy is transferred. And this term or this method of transfer of energy is conduction. So atom pass to other atoms and electrons, atoms and electrons as they pass and they move through the lattice, and electrons passes to other atoms or electrons as electrons moves through the lattice, or you can say the free electrons. Eventually the water reaches the boiling point. Thermal energy from hot plate is still being transferred to water. Explain in terms of molecule the effect of thermal energy of water. So now the external thermal energy which is being supplied to water. See, as the boiling point is reached, the temperature is not going to increase. The temperature will not increase. But the thermal energy which is supplied externally is used to break the bonds of the water molecule, and the water molecule will escape faster, or you can say will convert into vapor faster. So when the boiling point is reached, the temperature of the water will not increase. Thermal energy of water is used to break bonds of water. Now the thermal energy which is supplied externally to this, now it is being used to break the bond of water molecules, and the water molecules will escape faster, or you can say the conversion to vapor or converts into vapor at a more faster rate. So its thermal energy supplied to water is used to break bonds between water molecules, and the water molecules will escape faster. You can say they are converted to vapor. The mass of the water decreases by 0.11 kg in 300 seconds. The specific latent heat of vaporization of water is 2.3 × 10⁶ joules per kg. Calculate the rate at which the water gains thermal energy. We have to find the rate of gain of energy. See, we know that the total heat Q is equal to m into L, where m is the mass and L is the latent heat of vaporization. So mass is 0.11 and latent heat is 2.3 into 10⁶. So basically that is 253,000 joules. So this is the amount of energy which is released in 300 seconds. But what we have to do? We have to find the rate. So 253,000 joules. We know that the time is 300 seconds. In order to calculate rate, the total energy divided by time. So it's 253,000 divided by 300 seconds. So to find the rate is 253,000 divided by 300, which is actually 843.33. So you can round this off. You can round this off to 840 watts. That is 840 watts. That's the answer. Figure 5.1 shows the structure of liquid in glass thermometer. You see the bulb, liquid in glass. The bulb of a thermometer is placed into a beaker of warm water. As the liquid expands, it moves along the tube. Explain in terms of molecule why the liquid expands when heated. See, when the liquid is heated, its molecules gains kinetic energy and they start moving vigorously, pushing each other, which causes expansion. So that's exactly what you write. When the liquid is heated, its molecules gains kinetic energy. gain kinetic energy and start moving vigorously. Pushing starts moving vigorously. Pushing each other, which causes the expansion, or because of which the liquid expands. Which causes expansion. Explain in terms of molecule why a liquid expand more than a solid when heated. So you know that the force of attraction between the liquid molecules is comparatively less than that of solids. So for the same work done, liquid molecules will have greater separation. So what you will write is the force of attraction between liquid molecules is less than that of solid. So for the same work done, liquid molecule will have greater separation, because of which the liquid expands more than the solids. For same work done, liquid molecules have greater expansion. A second thermometer has a larger bulb that contains more of the same liquid than the thermometer shown in figure 5.1. It has a different scale. In every other way, it is identical. Okay. Explain how the sensitivity of the second thermometer compares with the sensitivity of thermometer in figure 5.1. Now see, the second thermometer is now having more volume, or you can say it has more liquid than the first one. Hence, it will move greater distance, making it more sensitive. So what you will write is second thermometer has more liquid than the first one. Hence will move greater distance as compared to the first one. So resulting in being more sensitive. So this thermometer will be more sensitive. So hence will move greater distance. Yeah, for 4-degree rise in temperature. You can write this also, yeah. For per degree rise in temperature, hence more sensitive. Explain how the range of second thermometer compares with the range of the thermometer in the figure 5.1. So this will have a smaller range. Now, see, it expands more for the same rise in temperature. So what will happen? If it is expanding more for the same rise in temperature, it is going to reach the tube end earlier. So that's why its range is reduced. So what you will write is smaller range, and it expands more for the same rise in temperature. Or you should remember that greater the bulb, smaller will be the range. Now state one everyday problem that is a result of thermal expansion. So you see the rail tracks. So rail tracks may bend due to thermal expansion. So this is one marker question. So just write rail tracks may bend due to thermal expansion. and yeah, thermal expansion. Suggest and explain one way of solving this problem. So basically the gaps between the rails tracks are left for the expansion of railway tracks, especially during summers. So these gaps actually allow them to expand. So gaps between the rail tracks are left for the expansion of rail tracks. For the expansion of rail tracks.